Hello friends, in this video we are going to look at the performance difference between TreeSet and ArrayList. Here we are going to prove how fast TreeSet will be when we are searching for a particular element. From the previous videos in the playlist, we know how TreeSet works. So TreeSet works based on the red-black tree. So that's the underlying data structure. Here we will compare the performance difference between TreeSet and ArrayList. So we will use the instant class from time package. So the instant class will record a time in a big integer value. So we can take a snapshot of 2 time interval. From the code we will get a 2 time interval t1 and t2 using this time instant class. Next we will give this 2 time instant class to the duration class. So the duration class represents the time difference between the 2 time instances t1 and t2. So we use these 2 class instances, I mean the time instant as well as a duration, to calculate the performance difference between the ArrayList as well as TreeSet. Alright, now let us go to the Eclipse demo and see how TreeSet performs faster than the ArrayList when we are searching for an element. So here is the example. Here first we declared 2 time instances from and to. Then at code snippet 2 what we are doing, here we are trying to add 9 million elements to ArrayList. So the element starts at 10 and it ends at 9 million minus 1. So approximately 9 million we can say. So before commencing this task, we are taking the snapshot. So it will give the snapshot in a big integer value. After that we are getting one more snapshot after performing this task. So this is t1 and this is t2. So here we named it as from and to. Then here if you see in the duration class we are passing these instances from and to duration.between. So this function called between will return a duration instance. Then from that we are making call to milliseconds, and this milliseconds will give the calculates the time difference in terms of milliseconds. That means we will get how many milliseconds elapsed for adding these 9 million elements in ArrayList. So this is our first code snippet, and in second code snippet we do the same, but here we create a TreeSet and add 9 million elements. Then we calculate the time instance the same way. So here once again we are getting 2 time stamp. Here this is the first time stamp and this one is the second time stamp. Then we are calculating the difference in milliseconds. So we can compare how much time it takes to add 9 million element in ArrayList as well as a TreeSet. So in ArrayList it's going to place the elements in continuous location. But in TreeSet it needs to compare the element and add. So we saw that in the previous video, right? So when we are adding the element, it will actually compass the element and it will keeps the element in sorted order, and at the same time it needs to do the task of balancing the tree. So all those overheads are here when compared to ArrayList. Alright. Next what we are doing, so we have same number of elements in both the data structure. ArrayList, so it employs the continuous memory location, and TreeSet it makes use of the red black tree and arranges the elements. Next, we pick 4 element. I mean, so we are making use of the contains method, and we are checking whether these elements exist in the collection. That means there are 9 million elements in the collection, and we are checking a predetermined 4 value that is available. So here we are doing this in ArrayList as well as in TreeList. So what we are searching is, we are searching the same element between these two. Then here we are calculating the time difference. Like before the search, we take one snapshot, and after finding all the 4 element with the contains, we are taking one more snapshot, but this time instead of millisecond, we are calculating it in nanoseconds. Yeah, here we are doing that for the TreeSet. So I kept a breakpoint at 4 different interval, but whenever the breakpoint hit, it won't disturb the time instances from 1 to 2. So when the breakpoint hit, by the time we calculated the proper from 1 to 2, that means T1 and T2. Same case here, and same in all other cases. We just kept after calculating the 2. Alright, now let us execute and see how it works. So breakpoint is hit, and if I execute this, it will say that array created in 2800 or 2900 milliseconds. That means almost approximately 3 seconds. So it's millisecond, right? So this one is second. Since it's 8, I am taking it as a 3 second to add all the elements. I mean, add 9 million element in ArrayList. Next, so we should not debug. If you click step over, then we will miss the correct timestamp entries. So just running it, it will halt here next. So now it ended. So if you look at here, the construction of a red black tree took almost 9 seconds. 9 seconds. So we already told what is the overhead, because it needs to arrange the element, it needs to sort, and as well as it needs to balance the tree. So that's the time difference during the construction. Now we are performing the search here. First we are doing the search in ArrayList. So if you see here, so it found all 4 elements. So it said I found true, true, true. And if you look at search elements, took this many nanoseconds. So if I cut these 3, this many microseconds and 84 millisecond to find all 4 elements. So that's what the ArrayList took. Now let us do this for red black tree, that means the TreeSet. So it took just 0 nanoseconds. So now you can see the difference. So this many nanoseconds, not even 1 nanosecond here in a TreeSet. Maybe if you search more number of elements, then you may get some 3 or 4 nanoseconds. So in the demo we saw that how fast TreeSet will be when compared to ArrayList. However, while adding the element, we saw there will be some overhead because of the construction of binary search tree and balancing it to be in compliant with red block tree. That's all in this video. Thank you for watching. Bye.